The gentle dance of our planet through the cosmos holds secrets that have captivated humanity since we first looked up at the night sky. Earth spins on its axis like a cosmic ballerina, completing one full rotation every 24 hours. This spinning motion creates the cycle of day and night that governs all life on our planet. But here is something truly remarkable. Our planet is not spinning at a constant speed. The rotation of Earth is gradually slowing down, losing about 1.7 milliseconds per century. This might seem insignificant, but over millions of years, it adds up considerably. Ancient records from civilizations like the Babylonians show that days were slightly shorter in their time compared to ours. The primary cause of this slowdown is the gravitational pull of the moon creating tidal friction. As ocean waters move across the seafloor due to tidal forces, they create friction that acts like a brake on Earth's rotation. Scientists have discovered that 600 million years ago, a day on Earth lasted only 21 hours. Looking far into the future, days will continue to lengthen until eventually Earth will show only one face to the moon, just as the moon currently shows only one face to Earth. This process, called tidal locking, happens because the moon is also pulling on the solid body of Earth, creating bulges in the crust itself. The energy lost from Earth's rotation does not simply disappear, but transfers to the moon, pushing it gradually farther away from our planet at a rate of about 3.8 centimeters per year. This cosmic dance between Earth and Moon demonstrates how nothing in space remains truly static, and even the length of our days evolves over geological timescales. Look up on a clear night, and you might wonder what lies beyond our atmosphere. The boundary between Earth's atmosphere and space is not as clear-cut as you might imagine. There is no solid line where air ends and space begins, but rather a gradual transition zone. Scientists have designated an arbitrary boundary called the Kármán line at 100 kilometers above sea level as the official edge of space. However, the atmosphere does not simply stop there. Traces of atmospheric gases extend far beyond this point, reaching out thousands of kilometers into what we consider space. The atmosphere consists of several distinct layers, each with unique characteristics. Starting from the ground, we have the troposphere where all weather occurs, extending up to about 12 kilometers. Above that lies the stratosphere, home to the protective ozone layer that shields us from harmful ultraviolet radiation. The mesosphere comes next, where most meteors burn up as they enter our atmosphere, creating the shooting stars we see streaking across the night sky. Beyond that is the thermosphere, where temperatures can soar to over 1,000 degrees Celsius, though you would not feel hot there because the air is so thin. The outermost layer, the exosphere, gradually fades into the vacuum of space. Satellites orbit in various layers depending on their purpose. The International Space Station orbits in the thermosphere, between 330 and 430 kilometers up, where it experiences enough atmospheric drag to require occasional boosts to maintain altitude. Some particles from our atmosphere reach as far as 10,000 kilometers above Earth, creating a fuzzy boundary with interplanetary space. This extended atmosphere interacts with solar wind and radiation, creating phenomena like auroras when charged particles collide with atmospheric gases near the poles. The moon hangs in our sky as a constant companion, yet its influence extends far beyond its serene appearance. Without the moon, life on Earth would be dramatically different if it could exist at all. The most obvious effect of the moon is the creation of ocean tides. Twice each day, the gravitational pull of the moon creates bulges in Earth's oceans, causing the rhythmic rise and fall of tides that shape coastal ecosystems around the world. But the moon's influence goes much deeper than just moving water. The moon acts as a cosmic stabilizer for Earth's axial tilt. Our planet currently tilts at 23.5 degrees relative to its orbital plane around the sun, giving us our seasons. Without the moon's gravitational influence, this tilt would vary wildly over time, swinging anywhere from 0 to 85 degrees. Mars, which has only tiny moons with negligible gravitational effects, experiences exactly this kind of chaotic axial variation. Such dramatic shifts in tilt would create catastrophic climate changes, making it nearly impossible for complex life to evolve. The moon also affects Earth's rotation speed, as we discussed earlier, which influences everything from weather patterns to the length of the seasons. Marine life particularly depends on the moon's tidal rhythms. Countless species time their reproduction, feeding, and migration patterns to the lunar cycle. Coral reefs spawn in sync with the moon. Sea turtles nest according to lunar phases, and many fish species navigate using the moon's light. Even land animals, including humans, may be influenced by lunar cycles in ways we are only beginning to understand. The Moon formed about 4.5 billion years ago, most likely when a Mars-sized object called Theia collided with the young Earth, ejecting debris that eventually coalesced into our satellite. Our Sun appears as a simple ball of light in the sky, but it is actually an incredibly complex nuclear furnace. Every second, the Sun converts approximately 600 million tons of hydrogen into helium through nuclear fusion in its core. This process releases an enormous amount of energy, producing more power in 1 second than humanity has used throughout all of history. The light we see from the Sun actually began its journey in the core, but it takes a surprisingly long time to reach us. Photons created in the Sun's core bounce around inside the star for anywhere from 10,000 to 170,000 years before finally reaching the surface. Once a photon escapes the surface, it takes only 8 minutes and 20 seconds to travel the 150 million kilometers to Earth. The Sun is not a solid body, but rather a sphere of superheated plasma held together by its own gravity. Different parts of the Sun rotate at different speeds, with the equator completing a rotation in about 25 days, while the poles take about 34 days. This differential rotation creates complex magnetic fields that manifest as sunspots, solar flares, and coronal mass ejections. Sunspots are areas of intense magnetic activity that appear darker because they are cooler than surrounding regions, though still at a scorching temperature of about 3,700 degrees Celsius. The Sun goes through an 11-year cycle of activity, with the number of sunspots rising and falling in a predictable pattern. During solar maximum, the Sun produces more solar flares and coronal mass ejections, which can disrupt satellites, power grids, and communication systems on Earth. The Sun has been burning for about 4.6 billion years and has enough fuel to continue for another 5 billion years before expanding into a red giant that will likely engulf. Earth-Venus shines brilliantly in our evening and morning sky, sometimes called the evening star or morning star despite being a planet. This dazzling world is often considered Earth's twin because of similar size and mass, but the similarities end there. Venus is the hottest planet in our solar system, with surface temperatures reaching 470 degrees Celsius, hot enough to melt lead. What makes this even more remarkable is that Venus is not the closest planet to the Sun. Mercury holds that distinction. Venus achieves its extreme temperatures through a runaway greenhouse effect. The planet's thick atmosphere, composed mainly of carbon dioxide with clouds of sulfuric acid, traps heat so effectively that temperatures remain constant day and night at the equator and poles. The atmospheric pressure on Venus is 92 times greater than Earth's, equivalent to being 900 meters underwater in Earth's oceans. This crushing pressure would instantly kill any unprotected human who somehow survived the temperature. Venus rotates in the opposite direction to most planets, a phenomenon called retrograde rotation. Scientists believe a massive collision early in the planet's history may have knocked Venus onto its side or completely flipped it over. Even more unusual, Venus rotates extremely slowly, taking 243 Earth days to complete one rotation. Meanwhile, it takes only 225 Earth days to orbit the Sun. This means a day on Venus is actually longer than a year on Venus. If you could stand on Venus's surface and somehow survive, you would see the Sun rise in the west and set in the east. The Soviet Venera probes managed to land on Venus and survived just long enough to send back a few images before being destroyed by the hostile environment. These images revealed a rocky, barren landscape with an orange sky. Mars has captured human imagination for centuries as the most likely place in our solar system to find signs of life. The red planet gets its distinctive color from iron oxide, essentially rust covering much of its surface. Mars is about half the size of Earth, with gravity only 38% as strong. This lower gravity allowed ancient volcanic activity to build the largest volcano in the solar system, Olympus Mons, which towers 21 kilometers above the Martian plains and stretches 600 kilometers across. To put this in perspective, Olympus Mons is nearly 3 times the height of Mount Everest, and so vast that its base would cover roughly the area of Italy. Mars also features the longest and deepest canyon system in the solar system, Valles Marineris, stretching 4,000 kilometers long, 200 kilometers wide, and up to 7 kilometers deep. This colossal rift valley dwarfs Earth's Grand Canyon. Evidence suggests Mars once had liquid water flowing across its surface billions of years ago. Ancient riverbeds, lake basins, and even features that look like shorelines of vast oceans have been identified from orbit. Where did all this water go? Some remains frozen in polar ice caps and buried underground as permafrost. But much was lost to space when Mars lost its global magnetic field about 4 billion years ago. Without this protective shield, solar wind gradually stripped away much of Mars's atmosphere, dropping the air pressure so low that liquid water can no longer exist on the surface. Today, Mars has an atmosphere less than 1% as thick as Earth's, composed mainly of carbon dioxide. Despite the harsh conditions, Mars experiences weather including dust storms that can occasionally engulf the entire planet. These global dust storms can last for months, blocking out the sun and creating challenges for solar-powered rovers exploring the surface. Jupiter reigns as the king of planets, more massive than all other planets in our solar system combined. This gas giant is so large that 1,300 Earths could fit inside it, yet it rotates faster than any other planet, completing one rotation in less than 10 hours. This rapid rotation creates powerful winds that race around the planet at speeds exceeding 500 kilometers per hour, organizing into distinctive bands of clouds. The most famous feature on Jupiter is the Great Red Spot, a gigantic storm that has been raging for at least 350 years since astronomers first observed it. This storm is so enormous that 2 or 3 Earths could fit inside it. The Great Red Spot is essentially a high-pressure system similar to hurricanes on Earth. But unlike terrestrial storms that draw energy from warm ocean waters, Jupiter's storms are powered by the planet's internal heat. Jupiter radiates more heat into space than it receives from the Sun, essentially acting like a failed star. When Jupiter formed, it almost had enough mass to ignite nuclear fusion in its core and become a star itself. If Jupiter were about 80 times more massive, it would have become a second sun in our solar system. Despite being called a gas giant, Jupiter likely has a solid core of rock and ice beneath its thick atmosphere. The pressure deep inside Jupiter is so intense that hydrogen is compressed into a metallic form that conducts electricity. This metallic hydrogen layer, combined with Jupiter's rapid rotation, generates the strongest magnetic field of any planet, extending millions of kilometers into space. This powerful magnetosphere traps charged particles, creating intense radiation belts that would be deadly to unshielded spacecraft. Jupiter has at least 95 known moons, with 4 massive satellites called the Galilean moons visible through small telescopes. Saturn's magnificent rings make it perhaps the most visually stunning planet in our solar system. These rings appear solid from a distance, but consist of billions of individual particles ranging from dust-sized grains to house-sized boulders, all composed primarily of water ice. The rings extend outward from Saturn for hundreds of thousands of kilometers, yet remain remarkably thin, in some places only 10 meters thick. If you built a scale model of Saturn's rings using paper to represent their thickness, the rings would need to stretch several kilometers in diameter to maintain accurate proportions. Scientists debate how the rings formed, with 2 main theories dominating the discussion. The rings might be remnants of a moon that was destroyed by tidal forces or a collision, or they could be leftover material from Saturn's formation that never coalesced into a moon. Recent research suggests Saturn's rings might be much younger than the planet itself, perhaps only a few 100 million years old. The rings are not solid structures, but rather countless particles orbiting Saturn independently, each acting like a tiny moon. The gaps visible between rings are created by the gravitational influence of Saturn's many moons, which shepherd ring particles into distinct bands. Saturn itself is a gas giant like Jupiter, composed mainly of hydrogen and helium. The planet's density is so low that it would float if you could find a bathtub large enough to hold it. Saturn has the most extensive moon system in the solar system, with 83 confirmed moons and many more awaiting confirmation. The largest moon, Titan, is bigger than the planet Mercury and possesses a thick atmosphere, making it the only moon in our solar system with substantial air. Titan's atmosphere is primarily nitrogen, like Earth's, and it features weather patterns including clouds and rain, though the rain is liquid methane rather than water. Uranus rolls through space on its side, a cosmic oddity in our solar system. The planet's axis is tilted 98 degrees, meaning it essentially orbits the Sun while lying on its side. This extreme tilt causes the most unusual seasons in the solar system. Each pole experiences 42 years of continuous sunlight, followed by 42 years of complete darkness. Scientists believe a massive collision with an Earth-sized object early in the solar system's history knocked Uranus onto its side. This impact was so violent that it may have also affected the planet's heat distribution. Unlike other planets that radiate more heat than they receive from the Sun, Uranus emits almost no excess heat, making it the coldest planet in our solar system, despite not being the farthest from the Sun. Temperatures in Uranus's atmosphere can drop to -224 degrees Celsius. Uranus appears as a pale blue-green disk due to methane in its atmosphere, which absorbs red light and reflects blue and green wavelengths. The planet is classified as an ice giant rather than a gas giant like Jupiter and Saturn because it contains more ices like water, ammonia, and methane rather than just hydrogen and helium. Uranus has faint rings, discovered only in 1977 when astronomers noticed stars dimming as they pass behind the planet. These rings are much darker and thinner than Saturn's spectacular ring system, composed of dark particles, possibly containing organic compounds. Uranus has 27 known moons, all named after characters from William Shakespeare's plays and Alexander Pope's poem, The Rape of the Lock. The 5 largest moons are Miranda, Ariel, Umbriel, Titania, and Oberon. Miranda shows some of the strangest terrain in the solar system, with cliffs up to 20 kilometers high and a patchwork surface suggesting the moon may have been shattered and reassembled by a massive impact. Neptune swirls with the fastest winds in the solar system, reaching speeds up to 2,000 kilometers per hour. This distant world appears as a brilliant blue sphere due to methane in its atmosphere. Neptune is the most distant planet from the Sun since Pluto was reclassified as a dwarf planet in 2006. This planet was not discovered through direct observation, but through mathematical predictions. Astronomers noticed irregularities in Uranus's orbit and calculated where another planet must be located to cause these perturbations. When telescopes were pointed at the predicted location, Neptune was discovered in 1846, a tremendous triumph for mathematical astronomy. Neptune takes 165 Earth years to complete a single orbit around the Sun, meaning it has completed only one full orbit since its discovery. The planet is nearly identical in size and composition to Uranus, earning both planets the classification of ice giants. Like Uranus, Neptune has a dynamic atmosphere with massive storm systems. The most famous was the Great Dark Spot, discovered by Voyager 2 in 1989, a storm system similar to Jupiter's Great Red Spot, but which had disappeared by the time Hubble Space Telescope observed Neptune 5 years later. This demonstrates that Neptune's weather patterns change more rapidly than Jupiter's. Neptune's largest moon, Triton, is particularly fascinating because it orbits the planet backward, opposite to Neptune's rotation. This retrograde orbit proves Triton was not formed alongside Neptune, but was captured from the Kuiper Belt, a region of icy bodies beyond Neptune's orbit. Triton is geologically active despite its extreme distance from the Sun, with geysers erupting nitrogen gas and ice particles several kilometers into its thin atmosphere. Triton's surface temperature reaches -235 degrees Celsius, making it one of the coldest surfaces in the solar system. Pluto's story reminds us that science constantly evolves as we learn more about our universe. Once considered the 9th planet, Pluto was reclassified as a dwarf planet in 2006, a decision that sparked considerable debate. The reclassification occurred not because scientists learned anything new about Pluto itself, but because they discovered many similar objects in the outer solar system. When astronomers found Eris, an object slightly more massive than Pluto, they faced a choice: either add potentially dozens of new planets as more were discovered, or create a new category. The International Astronomical Union defined 3 criteria for planetary status: orbiting the Sun, having sufficient mass to assume a spherical shape, and having cleared the neighborhood around its orbit. Pluto meets the first 2 criteria, but fails the third, sharing its orbital zone with thousands of other Kuiper Belt objects. Despite its reclassification, Pluto remains a fascinating world. When the New Horizons spacecraft flew past Pluto in 2015, it revealed a complex, geologically active world, far more interesting than the dead ice ball scientists expected. Pluto's most distinctive feature is a heart-shaped region informally named Tombor Regio after Pluto's discoverer. This region contains Sputnik Planitia, a vast plain of nitrogen ice that appears to be relatively young, suggesting Pluto has active geology despite being so far from the Sun. Mountains of water ice tower several kilometers high, and there is evidence of flowing nitrogen glaciers. Pluto has 5 known moons, with Charon being by far the largest, measuring more than half Pluto's diameter. The Pluto-Charon system is sometimes considered a double planet because the center of mass around which both objects orbit lies outside Pluto itself. Pluto and Charon are tidally locked to each other, always showing the same face to one another as they orbit their common center of mass every 6.4 days. Asteroids are rocky remnants from the early solar system, offering clues about planetary formation. Most asteroids orbit in the asteroid belt between Mars and Jupiter, a region containing millions of objects ranging from dust particles to Ceres, a dwarf planet nearly 1,000 kilometers in diameter. The total mass of all asteroids combined is less than our Moon, dispersed across a vast region of space. Contrary to popular depictions in movies, the asteroid belt is mostly empty space. If you were floating in the asteroid belt, you likely would not see another asteroid with the naked eye. Spacecraft routinely pass through the asteroid belt without incident, requiring no special maneuvering to avoid collisions. Asteroids come in various types depending on their composition. Some are metallic, composed primarily of iron and nickel, likely fragments from the cores of larger objects that broke apart during collisions. Others are rocky, similar to Earth's crust, while some are carbonaceous, containing water and organic compounds. These carbonaceous asteroids are particularly interesting to scientists because they preserve material from the very earliest days of the solar system, unchanged for over 4 billion years. Some scientists believe these asteroids delivered water and organic molecules to Earth during the late heavy bombardment, possibly providing the building blocks necessary for life to emerge. Asteroids occasionally leave their orbits and head toward Earth. An asteroid measuring 10 kilometers across struck Earth 66 million years ago, creating the Chicxulub crater in Mexico and causing the extinction of the dinosaurs, along with 75% of all species. Modern astronomers actively track near-Earth asteroids, cataloging objects that might pose a threat. Several missions have visited asteroids up close, including spacecraft that landed on asteroids and collected samples. The Japanese Hayabusa missions successfully returned material from asteroids Itokawa and Ryugu, while NASA's OSIRIS-REx brought back samples from asteroid Bennu, providing pristine material from the dawn of the solar system. Comets are cosmic snowballs composed of frozen gases, rock and dust that orbit the sun. When a comet's orbit brings it close to the sun, solar radiation causes the frozen material to sublimate directly from solid to gas, creating the comet's characteristic tail. Comets actually develop two distinct tails: a dust tail that curves along the comet's orbit, and an ion tail of charged particles that always points directly away from the sun, pushed by the solar wind. Some comets develop tails millions of kilometers long, visible across Earth's sky. The solid nucleus of a comet is relatively small, typically a few kilometers across, but the tail and surrounding gas envelope called the coma can be larger than the sun. Comets come from two main regions in the outer solar system. Short-period comets that orbit the sun in less than 200 years come from the Kuiper Belt, a region beyond Neptune's orbit containing thousands of icy bodies. Long-period comets with orbital periods of thousands or even millions of years come from the Oort cloud, a spherical shell of icy objects surrounding the solar system at distances up to 100,000 astronomical units. The Oort cloud has never been directly observed, but must exist to explain where long-period comets originate. Occasionally, gravitational perturbations from passing stars or other objects nudge an Oort cloud object toward the inner solar system, beginning its journey that may take millions of years. Famous comets like Halley's Comet have been observed for thousands of years, with records dating back to ancient civilizations. Halley's Comet returns to the inner solar system every 75 to 76 years, last appearing in 1986 and due to return in 2061. Each time a comet passes near the sun, it loses material, gradually shrinking. Eventually, comets either break apart completely or exhaust their volatile ices, becoming inactive rocky bodies indistinguishable from asteroids. Some meteor showers occur when Earth passes through the debris trail left by a comet, causing numerous shooting stars as tiny particles burn up in our atmosphere. Meteors streak across our night sky as shooting stars, creating brief flashes of light that have inspired wishes and wonder for millennia. These are not actually stars, but tiny particles, often no larger than grains of sand, burning up as they enter Earth's atmosphere at tremendous speeds. The friction with air molecules heats these particles to thousands of degrees, causing them to glow brightly for a few seconds before completely vaporizing. Meteors that survive the journey through the atmosphere and land on Earth's surface are called meteorites, and they provide scientists with invaluable samples of material from other worlds. Most meteorites come from asteroids, though a few rare specimens come from the Moon or Mars, blasted off those worlds by impacts and eventually falling to Earth. Scientists have identified over 50,000 meteorites, with Antarctica being a particularly good place to find them, because dark meteorites stand out against the white ice. Studying meteorites reveals information about the early solar system that cannot be obtained any other way. The oldest meteorites date back 4.567 billion years, giving us the age of the solar system itself. Some meteorites contain tiny grains that predate the solar system entirely, remnants of stars that died before our sun was born. These pre-solar grains have different isotopic compositions than solar system material, proving they formed elsewhere. Other meteorites contain amino acids and other organic molecules, supporting the theory that life's building blocks may have been delivered to Earth from space. Large meteorite impacts have shaped Earth's history. The most famous extinction event occurred 66 million years ago, but Earth has experienced several other mass extinctions, likely caused or contributed to by impacts. Scientists now recognize that asteroid and comet impacts are not rare on geological timescales. The craters are often hidden by erosion, vegetation, or geological processes, but over 190 confirmed impact craters have been found on Earth. The threat of future impacts is taken seriously enough that space agencies monitor near-Earth objects and have developed plans to deflect any asteroid found, to be on a collision course with Earth. The Milky Way stretches across our night sky as a luminous band of light, our home galaxy containing hundreds of billions of stars. We live inside this vast cosmic structure, giving us a unique perspective, but also making it challenging to map the galaxy's true shape. Ancient Greeks called it Galaxias Kyklos, meaning milky circle, because it appears as a milky band arcing across the sky. Only in the 20th century did astronomers prove that this band of light is actually our view of the galaxy's disk from inside. The Milky Way is a barred spiral galaxy, meaning it has a central bar-shaped structure of stars with spiral arms extending from the ends of this bar. Our Sun resides about halfway out from the galactic center, in a minor spiral arm called the Orion Arm, or local spur. The galaxy rotates, with our Sun taking approximately 230 million years to complete one orbit around the galactic center. This means that since the dinosaurs became extinct, our solar system has traveled only a fraction of one galactic orbit. The Milky Way measures about 100,000 light-years across, but only 1,000 light-years thick, giving it a disc-like shape with a bulge in the middle. At the very center of the galaxy lies a supermassive black hole named Sagittarius A star, containing about 4 million times the Sun's mass. Radio observations reveal that this black hole is currently quiet, consuming only small amounts of material, but X-ray observations show evidence of past activity. The galaxy is not alone in space, but belongs to a collection of galaxies called the Local Group, which includes the Andromeda Galaxy, the Triangular Galaxy, and about 80 smaller galaxies. The Milky Way and Andromeda are the two dominant members of this group, and they are approaching each other at about 120 kilometers per second. In about 4.5 billion years, these two galaxies will collide and merge, creating a new elliptical galaxy that some astronomers have nicknamed Milkomeda. Black holes represent the most extreme objects in the universe, regions of spacetime where gravity is so powerful that nothing, not even light, can escape. Despite their fearsome reputation, black holes are actually quite simple objects, characterized by only three properties: mass, electric charge, and spin. Everything else about the matter that fell into the black hole is lost forever, a concept physicists call the no-hair theorem. Black holes form when massive stars exhaust their nuclear fuel and collapse under their own gravity. The star's core compresses to an infinitely small point called a singularity, surrounded by an invisible boundary called the event horizon. Anything crossing the event horizon is lost forever, unable to return to the outside universe. The event horizon size depends on the black hole's mass. A black hole with the Sun's mass would have an event horizon only 6 kilometers across, while supermassive black holes at galactic centers have event horizons larger than our solar system. Near a black hole, strange things happen to space and time. Gravity is so strong that it warps space-time, causing time dilation. An observer watching someone fall toward a black hole would see the person move slower and slower as they approach the event horizon, never quite seeing them cross it. The falling person, however, would experience time normally and would cross the event horizon in a finite amount of time, though they would not notice anything special at the moment of crossing. Inside the event horizon, the paths through space-time all lead to the singularity, making it as impossible to avoid as it is to avoid moving forward in time in normal space. The intense gravitational gradient near a black hole would stretch any object falling in, a process colorfully named spaghettification. Black holes are not cosmic vacuum cleaners indiscriminately sucking in everything around them. If our sun suddenly became a black hole of equal mass, Earth would continue orbiting exactly as before, experiencing no change in gravitational pull. We would freeze in the darkness, but we would not be sucked into the black hole. Neutron stars pack incredible density into a small space, creating some of the most extreme conditions in the universe. These stellar remnants form when massive stars explode as supernovae, leaving behind a core that collapses into an object about 20 kilometers across but containing more mass than our sun. A sugar cube-sized piece of neutron star material would weigh about 100 million tons on Earth, or roughly the weight of Mount Everest. Neutron stars achieve this density because the gravitational pressure is so intense that electrons and protons are crushed together, forming neutrons. In essence, a neutron star is a single atomic nucleus 20 kilometers across. The surface gravity of a neutron star is about 2 billion times stronger than Earth's gravity. Anything falling onto a neutron star would impact with such force that its atoms would be completely destroyed. Neutron stars rotate rapidly, sometimes spinning hundreds of times per second. This rapid rotation combines with intense magnetic fields to create pulsars, neutron stars that emit beams of radiation from their magnetic poles. As the neutron star rotates, these beams sweep through space like a cosmic lighthouse. When the beams point toward Earth, we detect regular pulses of radiation, hence the name pulsar. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, who initially wondered if the regular pulses might be signals from extraterrestrial intelligence. Pulsars are incredibly precise clocks, with some maintaining regularity, rivaling atomic clocks. This precision makes them useful for testing fundamental physics, including Einstein's theory of general relativity. Some neutron stars exist in binary systems with another star. If the companion star gets too close, the neutron star's intense gravity strips away the companion's outer layers, pulling matter onto the neutron star. This infalling matter heats up to millions of degrees, emitting X-rays and sometimes causing thermonuclear explosions on the neutron star's surface. These X-ray bursts can briefly outshine entire galaxies. Supernovae are among the most energetic events in the universe, releasing more energy in a few seconds than our sun will emit during its entire lifetime. These stellar explosions occur in two main ways. In one scenario, a massive star exhausts its nuclear fuel and can no longer support itself against gravitational collapse. The core collapses in less than a second, rebounding in a catastrophic explosion that blows the star apart. In another scenario, a white dwarf in a binary system accumulates matter from a companion star until it reaches a critical mass, triggering runaway nuclear fusion that completely destroys the white dwarf. Both types of supernovae can briefly outshine entire galaxies, becoming visible across intergalactic distances. The explosion creates a rapidly expanding shockwave that plows through space at thousands of kilometers per second. This shockwave enriches the interstellar medium with heavy elements created in the star's core, and during the explosion itself, all elements heavier than iron are created in supernovae, meaning that the gold in jewelry, the uranium in nuclear reactors, and many other heavy elements were forged in stellar explosions. Supernovae play a crucial role in galaxy evolution, injecting energy and heavy elements into the interstellar medium, triggering new star formation and shaping the structure of galaxies. After a supernova explosion, the ejected material continues expanding, forming a supernova remnant. These remnants can remain visible for thousands of years, appearing as delicate filaments and shells of glowing gas. The Crab Nebula, remnant of a supernova observed in 1054, remains one of the most studied objects in the sky. Ancient Chinese and Arab astronomers recorded this supernova as a guest star, bright enough to be visible during the day. Supernovae in our own galaxy are relatively rare, occurring perhaps 2 or 3 times per century. The last observed supernova in the Milky Way occurred in 1604, studied by Johannes Kepler. Since then, Dust in the galactic plane may have hidden other supernovae from view. White dwarfs represent the final fate awaiting most stars, including our Sun. These stellar remnants form when stars similar to our Sun exhaust their nuclear fuel and shed their outer layers, leaving behind a hot, dense core about the size of Earth. Despite their small size, white dwarfs contain roughly the mass of the Sun, making them incredibly dense. A teaspoon of white dwarf material would weigh several tons on Earth. This extreme density is possible because white dwarfs are supported by electron degeneracy pressure, a quantum mechanical effect that prevents the electrons from being compressed closer together. Unlike main sequence stars that generate energy through nuclear fusion, white dwarfs produce no new energy. They simply radiate away their residual heat over billions of years. When a white dwarf forms, its surface temperature exceeds 100,000 degrees Celsius, giving off intense white or blue-white light. Over time, the white dwarf cools and dims, eventually becoming a black dwarf, though the universe is not yet old enough for any black dwarfs to exist. The coolest and dimmest white dwarfs currently known have surface temperatures around 3,000 degrees, still hotter than many stars. White dwarfs have a maximum possible mass called the Chandrasekhar limit, approximately 1.4 times the Sun's mass. If a white dwarf exceeds this limit, electron degeneracy pressure can no longer support it against gravity, and it will collapse further, either forming a neutron star or exploding as a Type Ia supernova. This mass limit makes Type Ia supernovae particularly useful for measuring cosmic distances because they all have roughly the same brightness at peak, serving as standard candles for mapping the universe. About 97% of all stars will end their lives as white dwarfs, including our Sun. In about 5 billion years, when the Sun exhausts its hydrogen fuel, it will swell into a red giant, likely engulfing Mercury and Venus and possibly Earth. Eventually, it will puff off its outer layers, creating a planetary nebula, and leave behind a white dwarf core. Red giants are dying stars in the late stages of their evolution, swollen to enormous sizes as they exhaust their core hydrogen fuel. When a star like our Sun runs out of hydrogen in its core, nuclear fusion stops temporarily, and the core contracts under gravity. This contraction heats the core until hydrogen in a shell around the core ignites, producing even more energy than before. This extra energy causes the star's outer layers to expand dramatically. The Sun will eventually become a red giant, swelling to perhaps 100 times its current diameter, possibly engulfing Earth's orbit. Red giants are cool stars with surface temperatures between 3,000 and 4,000 degrees Celsius, giving them their distinctive red color. Despite their lower surface temperatures, red giants are incredibly luminous because of their enormous surface area. A typical red giant might be hundreds or thousands of times more luminous than the Sun. The star Betelgeuse in the constellation Orion is a red supergiant so large that if placed where our Sun is, it would extend beyond the orbit of Mars. In late 2019 and early 2020, Betelgeuse dramatically dimmed, leading to speculation that it might be about to explode as a supernova. The dimming turned out to be caused by dust ejected from the star blocking some of its light, but Betelgeuse will indeed explode someday, though possibly not for thousands of years. When it does, it will be visible during the day and could be as bright as the moon for several weeks. Red giants lose mass through powerful stellar winds, shedding their outer layers into space. This material enriches the interstellar medium with heavy elements created through nuclear fusion during the star's life. Some red giants create spectacular planetary nebulae when they finally shed their outer envelopes. Despite the name, planetary nebulae have nothing to do with planets. Early astronomers thought they looked like the disks of planets through their telescopes. These nebulae display incredible variety and beauty, with shapes ranging from simple spheres to complex bipolar structures, butterfly shapes, and intricate patterns. Brown dwarfs are cosmic misfits, objects that formed like stars, but lack sufficient mass to sustain hydrogen fusion in their cores. They occupy the gap between the largest planets and the smallest stars, with masses ranging from about 13 to 80 times Jupiter's mass. Below 13 Jupiter masses, objects cannot even fuse deuterium, a heavy isotope of hydrogen, and are considered planets. Above 80 Jupiter masses, objects have enough mass and core temperature to fuse regular hydrogen, becoming true stars. Brown dwarfs fuse deuterium for a brief period when young, but this process lasts only a few million years. After the deuterium is exhausted, Brown dwarfs simply cool and fade away over billions of years. They remain hot enough to glow in infrared light, though they are very dim in visible light. Finding brown dwarfs proved challenging because they are so faint. The first confirmed brown dwarf was not discovered until 1995. Since then, hundreds have been found, with surveys suggesting they may be almost as common as stars. Brown dwarfs have some characteristics of planets and some of stars. Like planets, they have weather patterns, clouds, and possibly even auroras. Observations suggest some brown dwarfs have clouds made of molten iron or silicate minerals, creating storms of hot sand and liquid metal. Like stars, brown dwarfs are composed primarily of hydrogen and helium, and retain the composition of the cloud from which they formed. The coolest brown dwarfs discovered have temperatures below 100 degrees Celsius, cool enough that water vapor can exist in their atmospheres. These cool brown dwarfs blur the line between planets and stars even further. Some astronomers debate whether very large planets like Jupiter should be considered similar to brown dwarfs. Jupiter generates more heat than it receives from the Sun through gravitational contraction, similar to brown dwarfs, and both have similar compositions. The main difference is formation. Jupiter formed in a disk around the Sun from solid material that accumulated gas, while brown dwarfs formed directly from collapsing gas clouds like stars. Exoplanets orbit stars other than our Sun, and their discovery has revolutionized our understanding of planetary systems. For centuries, philosophers debated whether other stars had planets, but technology to detect them did not exist. The first confirmed exoplanet around a Sun-like star was discovered in 1995, though earlier discoveries had been made around pulsars. Since then, over 5,000 exoplanets have been confirmed, with thousands more candidates awaiting confirmation. These discoveries revealed that planetary systems are common and incredibly diverse, with many configurations unlike anything found in our solar system. Detection methods vary, but the most successful has been the transit method, which watches for the slight dimming of a star when a planet passes in front of it. The Kepler Space Telescope used this method to discover thousands of exoplanets before it ran out of fuel. The transit method works best for large planets orbiting close to their stars. So many early discoveries were hot Jupiters, gas giants orbiting closer to their stars than Mercury orbits our Sun. These worlds challenge theories of planetary formation because gas giants were thought to form far from stars where it is cool enough for ices to exist. Scientists now believe hot Jupiters formed farther out and migrated inward. Another detection method measures the wobble in a star's motion caused by an orbiting planet's gravitational pull. This radial velocity method has discovered hundreds of exoplanets and can detect planets that do not transit their stars. Combining both methods provides information about a planet's size and mass, allowing scientists to calculate its density and make educated guesses about composition. Some exoplanets orbit in the habitable zone, the region around a star where liquid water could exist on a planet's surface. These planets are of particular interest in the search for extraterrestrial life. One of the most exciting discoveries is the TRAPPIST-1 system, where 7 Earth-sized planets orbit a cool red dwarf star, with 3 or 4 potentially in the habitable zone. The search for extraterrestrial life captivates scientists and the public alike. Are we alone in the universe, or does life exist elsewhere? The question has profound implications for our understanding of biology, planetary science, and our place in the cosmos. Scientists focus on finding life in our solar system and on exoplanets around other stars. In our solar system, Mars is a prime target because it once had liquid water on its surface and possibly conditions suitable for life. Multiple missions have searched for signs of past or present life on Mars. The Perseverance rover currently explores Jezero Crater, an ancient lake bed, collecting samples that may eventually be returned to Earth for detailed analysis. Other potential habitats exist in unexpected places. Jupiter's moon. Europa has a global ocean beneath its icy crust, containing more water than all of Earth's oceans combined. Tidal forces from Jupiter's gravity heat Europa's interior, possibly creating hydrothermal vents on the ocean floor similar to those on Earth that support rich ecosystems. Saturn's moon Enceladus also has a subsurface ocean and actively shoots geysers of water into space, which the Cassini spacecraft flew through and analyzed. The water contains organic molecules and signs of hydrothermal activity, making Enceladus another promising place to search for life. Beyond our solar system, the search focuses on potentially habitable exoplanets. The next generation of telescopes, including the James Webb Space Telescope, can analyze exoplanet atmospheres for biosignatures, gases that might indicate life. Oxygen, when found with other gases like methane, could suggest biological activity. However, distinguishing true biosignatures from abiotic processes that can produce similar gases remains challenging. Some scientists search for technological signatures of intelligent civilizations. The search for extraterrestrial intelligence, or SETI, listens for radio signals or other signs of technology from space. Despite decades of searching, no confirmed signals have been detected, leading to the famous Fermi paradox. If intelligent life is common, where is everybody? Various solutions have been proposed, from the possibility that intelligent life is extremely rare to the idea that civilizations self-destruct before developing interstellar communication. Dark matter remains one of the greatest mysteries in physics, comprising about 85% of all matter in the universe, yet remaining completely invisible and undetectable except through its gravitational effects. Scientists discovered dark matter by observing that galaxies and galaxy clusters contain far more mass than can be accounted for by visible matter. In the 1970s, astronomer Vera Rubin measured the rotation speeds of stars in galaxies and found that stars far from galactic centers were moving much faster than expected. According to Newton's laws, stars farther from the center should orbit more slowly, just as outer planets in our solar system orbit more slowly than inner planets. Instead, stars throughout galaxies maintain roughly constant speeds, suggesting that galaxies are embedded in massive halos of invisible matter. Multiple lines of evidence now confirm dark matter's existence. Gravitational lensing, where massive objects bend light from more distant objects, shows that galaxy clusters contain far more mass than their visible matter. The cosmic microwave background radiation contains patterns that only make sense if dark matter exists. Computer simulations of galaxy formation fail to produce realistic galaxies without including dark matter. Despite knowing dark matter exists, scientists do not know what it is made of. It does not interact with electromagnetic radiation, making it invisible to all forms of light. It does not absorb, emit, or reflect light, passing through normal matter as if it were not there. Dark matter only interacts through gravity and possibly through the weak nuclear force. Many candidates have been proposed, with weakly interacting massive particles, or WIMPs, being a favorite for years. Experiments around the world search for dark matter particles, using detectors deep underground to shield them from cosmic rays. So far, no direct detection has been confirmed. Alternative theories suggest modifying our understanding of gravity rather than invoking invisible matter. But these theories struggle to explain all observations. Understanding dark matter is crucial because it shaped the evolution of the universe, providing gravitational scaffolding around which normal matter could collapse to form galaxies and large-scale structures. Dark energy poses an even deeper mystery than dark matter, comprising about 68% of the universe's total energy. Discovered in 1998, dark energy was completely unexpected and contradicted prevailing assumptions about the universe's fate. Astronomers studying distant supernovae as standard candles to measure cosmic expansion made an astonishing discovery. The universe's expansion is not slowing down due to gravity as expected, but is accelerating. This acceleration requires some form of energy pervading all of space, pushing the universe apart. Scientists named this mysterious energy dark energy because they have no idea what it actually is. Several theories attempt to explain dark energy. The simplest explanation is that dark energy is the cosmological constant, an intrinsic property of space itself. Einstein originally introduced the cosmological constant into his equations of general relativity to create a static universe, though he later called it his biggest blunder after learning the universe expands. Ironically, the cosmological constant may exist after all, explaining dark energy. If dark energy is the cosmological constant, then every cubic centimeter of space contains a tiny amount of energy. As the universe expands and creates new space, the total amount of dark energy increases. This leads to exponential expansion, with the universe expanding faster and faster over time. Alternative theories propose that dark energy is not constant but changes over time, a concept called quintessence. Testing these theories requires precise measurements of the universe's expansion rate throughout cosmic history. The existence of dark energy has profound implications for the universe's ultimate fate. If dark energy remains constant or grows stronger, the universe will continue accelerating forever. Galaxy clusters will become isolated as the space between them expands faster than light can cross it. Eventually, even galaxies will be torn apart as expansion accelerates. In the most extreme scenario, called the Big Rip, even atoms will eventually be torn apart as expansion becomes infinitely fast. This would occur about 22 billion years in the future if dark energy strengthens in a particular way. The Big Bang represents the beginning of our universe, occurring approximately 13.8 billion years ago. This was not an explosion in space, but rather an expansion of space itself. In the earliest moments, the entire universe was compressed into an infinitesimally small point of infinite density and temperature. Space and time themselves began with the Big Bang, making it meaningless to ask what happened before or what caused it. The laws of physics as we understand them break down at the moment of the Big Bang. In the first fraction of a second, the universe underwent a period of exponential expansion called inflation, during which it grew from smaller than an atom to macroscopic size. Inflation explains why the universe appears smooth and uniform on large scales and predicts the patterns of density variations that eventually formed galaxies and galaxy clusters. After inflation ended, the universe continued expanding and cooling. In the first few minutes, nuclear fusion occurred throughout the entire universe, creating the first atomic nuclei of hydrogen, helium, and trace amounts of lithium. These proportions match observations precisely, providing strong evidence for the Big Bang. For the first 380,000 years, the universe was opaque, filled with a hot plasma of electrons and nuclei. Light could not travel far before scattering off free electrons. When the universe cooled enough for electrons and nuclei to combine into neutral atoms, light could suddenly travel freely. This moment is called recombination, and the light released then is still traveling through the universe today as the cosmic microwave background radiation. Discovered accidentally in 1964 by Arno Penzias and Robert Wilson, the cosmic microwave background is the oldest light in the universe and provides a baby picture of the cosmos. Tiny temperature variations in this radiation, measured precisely by satellites, reveal the seeds of structure that grew into the galaxies and clusters we see today. The cosmic microwave background radiation is the oldest light we can observe, providing crucial insights into the early universe. This radiation fills all of space, coming from every direction equally. When first released 380,000 years after the Big Bang, this light was visible and orange-red in color. Over billions of years, as space expanded, the wavelengths of this light stretched, shifting it into the microwave portion of the electromagnetic spectrum. Today, the cosmic microwave background has a temperature of 2.7 degrees above absolute zero. The cosmic microwave background appears remarkably uniform, with the same temperature in all directions to better than 1 part in 100,000. This uniformity posed a problem for cosmologists, because regions of the sky separated by large distances have never been in contact, even at the speed of light, yet they have the same temperature. The theory of inflation solves this problem by proposing that the universe underwent exponential expansion very early, allowing regions that were initially in contact and equilibrated to be stretched to opposite sides of the observable universe. Despite its overall uniformity, the cosmic microwave background contains tiny temperature variations at the level of 1 part in 100,000. These variations represent density fluctuations in the early universe, regions that were slightly more or less dense than average. Denser regions had stronger gravity and eventually attracted matter to form galaxies and galaxy clusters, while less dense regions became cosmic voids. The pattern of these fluctuations encodes information about the universe's composition and geometry. Precise measurements by satellites like COBE, WMAP, and Planck have determined fundamental parameters of the universe with high accuracy. These measurements tell us the universe is 13.8 billion years old, has flat geometry on large scales, and consists of about 5% normal matter, 27% dark matter, and 68% dark energy. The cosmic microwave background also shows evidence of polarization patterns that could reveal gravitational waves from the inflationary epoch, though detecting these signals remains challenging. Gravity waves are ripples in spacetime itself, predicted by Einstein's general theory of relativity and directly detected for the first time in 2015. These waves are generated by accelerating massive objects, particularly by violent cosmic events like merging black holes or neutron stars. As gravity waves pass through space, they alternately stretch and compress spacetime, though the effect is extraordinarily tiny. The first detected gravity waves came from two black holes spiraling into each other and merging, an event that occurred about 1.3 billion light-years away. The collision released more energy than all the stars in the observable universe combined, though almost all of this energy was emitted as gravity waves rather than light. When these waves reached Earth, they caused detectors to change length by less than 1,000th the diameter of a proton. The detection required incredibly sensitive instruments called interferometers. The Laser Interferometer. Gravitational Wave Observatory, or LIGO, uses lasers to measure changes in the lengths of 4-kilometer-long arms to incredible precision. LIGO consists of 2 detectors separated by thousands of kilometers to distinguish real gravity wave signals from local vibrations and noise. Since the first detection, dozens of gravity wave events have been observed, mostly from merging black holes, but also from merging neutron stars. The detection of merging neutron stars was particularly exciting because it was observed both in gravity waves and across the electromagnetic spectrum, including gamma rays, X-rays, visible light, and radio waves. This multi-messenger astronomy provides far more information than either method alone. The collision of neutron stars creates heavy elements through rapid neutron capture, explaining the origin of much of the gold, platinum, and other heavy elements in the universe. Gravity wave astronomy has opened a new window on the universe, allowing scientists to observe events that produce little or no light. Future gravity wave detectors, including space-based instruments, will be even more sensitive and able to detect waves from more distant and less massive sources. Understanding gravity waves helps test Einstein's theory of general relativity under extreme conditions and provides information about the most violent events in the universe. The observable universe extends about 46.5 billion light-years in all directions from Earth, encompassing everything we can possibly see. This distance is greater than the universe's age of 13.8 billion years would suggest, because space itself has been expanding. Light from distant galaxies was emitted when those galaxies were much closer to us. During the billions of years the light traveled, space expanded, carrying those galaxies farther away. The most distant objects we can see emitted their light when the universe was very young, showing us what galaxies looked like billions of years ago. The observable universe is just a portion of the total universe. The universe may extend far beyond what we can see, possibly infinitely. Light from more distant regions has not had time to reach us yet, placing them beyond our cosmic horizon. As time passes, light from more distant regions reaches us, and the observable universe grows. However, because space's expansion is accelerating due to dark energy, there are regions of the universe whose light will never reach us. These regions are moving away faster than light can approach us due to the expansion of space itself. The observable universe contains an estimated 2 trillion galaxies, each containing billions to trillions of stars. The total number of stars in the observable universe may exceed 10 to the power of 24, vastly more than all grains of sand on all beaches on Earth. Despite this enormous number of stars and galaxies, the universe is mostly empty space. The distance between stars within galaxies is vast, and the space between galaxies is even more enormous. If you randomly placed a point anywhere in the universe, the chances of it being inside a star, planet, or any matter at all are infinitesimally small. The large-scale structure of the universe resembles a cosmic web, with galaxies arranged in filaments and sheets surrounding enormous voids. These voids, containing few or no galaxies, span hundreds of millions of light-years. The structure formed through gravitational collapse over billions of years, with dark matter providing the scaffolding around which normal matter collected to form galaxies. Time dilation is one of the most counterintuitive predictions of Einstein's theories of relativity. Both special relativity and general relativity predict that time is not absolute, but depends on motion and gravity. In special relativity, time slows down for objects moving at high speeds, relative to a stationary observer. This effect becomes significant only at speeds approaching the speed of light. At 90% of light speed, time passes at only about 44% of the rate for a stationary observer. This has been confirmed by experiments with atomic clocks on airplanes and satellites, which run slightly slower or faster depending on their speed and altitude. Astronauts on the International Space Station age slightly less than people on Earth, though the difference is only a few milliseconds over months in space. General relativity adds another twist. Time also slows down in stronger gravitational fields. Time passes more slowly near massive objects than in weaker gravity. This gravitational time dilation is not just theoretical, but must be accounted for in the global positioning system. Satellites orbit at high altitude, where gravity is weaker, causing their clocks to run faster than clocks on Earth's surface. Without correcting for both gravitational time dilation and the time dilation due to their orbital velocity, GPS coordinates would drift by several kilometers per day. Near extremely massive objects like black holes, time dilation becomes extreme. An observer watching someone fall toward a black hole would see them slow down as they approach the event horizon, with light from them becoming increasingly redshifted. The falling person would eventually appear frozen in time, never quite reaching the event horizon from the outside observer's perspective. However, from the falling person's viewpoint, they would cross the event horizon in finite time without noticing anything special at that moment. Time dilation means that time travel to the future is theoretically possible. By traveling at high speeds or spending time near a massive object, you would age more slowly than people elsewhere. Upon returning, you would find that more time had passed for everyone else than for you, effectively traveling into their future. The speed of light is the universe's ultimate speed limit, and nothing with mass can reach or exceed it. Light travels at exactly 299,792,458 meters per second in a vacuum, often rounded to 300,000 kilometers per second. This speed is not arbitrary but fundamental to the structure of space-time itself. Light always travels at this speed, regardless of the motion of the source or observer, a fact that seems paradoxical but is confirmed by countless experiments. This constancy of light speed led Einstein to develop special relativity. The speed of light connects space and time in relativity theory, explaining why time dilation and length contraction occur at high speeds. As an object with mass accelerates toward light speed, it gains energy and its mass effectively increases. Accelerating it further requires more and more energy, with infinite energy needed to actually reach light speed. This makes light speed an unbreachable barrier for massive objects. Light itself has no mass and always travels at light speed, never faster or slower in a vacuum. In materials like water or glass, light slows down, which causes refraction and allows lenses to focus light. However, even in materials, the light is still traveling at light speed between atoms. It just takes a longer path, interacting with atoms along the way. The finite speed of light means we see the universe as it was in the past. Light from the sun takes 8 minutes and 20 seconds to reach Earth, so we see the sun as it was 8 minutes ago. Light from the nearest star beyond the sun, Proxima Centauri, takes over 4 years to reach us. The most distant galaxies visible to powerful telescopes are seen as they existed billions of years ago when the universe was young. Looking deeper into space is looking back in time. This means we can observe the history of the universe by examining objects at different distances. The speed of light also limits how quickly information can travel, affecting everything from space exploration to communication with distant probes. Quantum mechanics governs the behavior of nature at the smallest scales, where particles behave very differently from everyday objects. At the quantum level, particles like electrons and photons exhibit wave-particle duality, behaving sometimes as particles and sometimes as waves. This dual nature is not just a limitation of our understanding, but a fundamental property of quantum objects. The famous double-slit experiment demonstrates this weirdness. When individual photons or electrons are sent through two slits, they create an interference pattern on a detector, indicating wave-like behavior. Yet when we observe which slit a particle goes through, the interference pattern disappears, and particles behave like particles. The act of measurement affects the outcome, suggesting that quantum objects do not have definite properties until measured. This leads to the uncertainty principle, formulated by Werner Heisenberg, which states that certain pairs of properties cannot both be precisely known simultaneously. The most famous example involves position and momentum. The more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. This is not due to measurement limitations, but is fundamental to nature. Quantum mechanics also predicts quantum entanglement, where two particles can be correlated such that measuring one instantly affects the other, regardless of the distance between them. Einstein called this spooky action at a distance, and believed it showed quantum mechanics was incomplete. However, experiments have confirmed that entanglement is real and does not violate relativity, because no information travels faster than light. Quantum mechanics has been extraordinarily successful in predicting experimental results and underlies much of modern technology, including transistors, lasers, and computer chips. Despite its success, debates continue about what quantum mechanics means for the nature of reality. Interpretations range from the Copenhagen interpretation, which states that particles do not have definite properties until measured, to the many worlds interpretation, which proposes that all possible measurement outcomes occur in separate branching universes. Antimatter is like a mirror image of normal matter, with particles that have opposite electrical charge but otherwise identical properties. For every type of particle, there exists a corresponding antiparticle. The antiparticle of the electron is the positron, identical in mass but with positive charge instead of negative. When a particle meets its antiparticle, they annihilate each other, converting their mass entirely into energy according to Einstein's equation E equals mc squared. This makes antimatter the most efficient possible fuel, converting 100% of mass into energy compared to nuclear fusion, which converts less than 1%. Despite antimatter's efficiency, it poses enormous practical challenges. Antimatter is rare in nature and incredibly difficult to produce and store. When antimatter touches any normal matter, immediate annihilation occurs, releasing gamma rays. This means antimatter must be stored without touching container walls, typically using magnetic fields to suspend charged antimatter particles in vacuum. Scientists at facilities like CERN produce tiny amounts of antimatter for research, though the quantities are measured in individual atoms. Producing just 1 gram of antimatter would require more energy than humanity generates in a year. One of the deepest mysteries in physics is why the universe contains matter but virtually no antimatter. According to our understanding of physics, the Big Bang should have created equal amounts of matter and antimatter. If this happened, everything would have annihilated, leaving a universe filled only with photons and no atoms, stars, or life. Something must have created a slight imbalance favoring matter over antimatter, allowing a tiny fraction of matter to survive. This asymmetry is called baryogenesis, and understanding it remains an active area of research. Several theories attempt to explain the matter-antimatter asymmetry, involving subtle differences in how matter and antimatter behave. Experiments have found small violations of symmetry in the decay of certain particles, but not enough to fully explain the universe's matter content. Solving this mystery could require discovering new physics beyond the standard model of particle physics. The Higgs boson, discovered in 2012 at CERN's Large Hadron Collider, is a fundamental particle that explains why other particles have mass. The Higgs boson is the quantum of the Higgs field, an invisible field that permeates all of space. Particles gain mass by interacting with this field, like objects moving through molasses. Particles that interact strongly with the Higgs field have large mass, while particles that barely interact have small or zero mass. Photons do not interact with the Higgs field at all, which is why they have no mass and travel at the speed of light. The Higgs mechanism is crucial to the standard model of particle physics, the theory describing all known fundamental particles and their interactions. Without the Higgs field, fundamental particles would have no mass, atoms could not form, and the universe would be radically different. The existence of the Higgs field was proposed in 1964 by several physicists, including Peter Higgs, to solve theoretical problems in particle physics. However, detecting the Higgs boson required building the world's largest and most powerful particle accelerator. The Large Hadron Collider accelerates protons to 99.999991% of the speed of light and smashes them together. These collisions recreate conditions similar to the early universe, briefly producing enormous energies in tiny volumes. Among billions of collisions, a few produce Higgs bosons, which exist for only a tiny fraction of a second before decaying into other particles. The Higgs discovery confirmed the standard model's predictions, but questions remain. Why does the Higgs field have the particular strength it does? Are there multiple Higgs bosons? The measured mass of the Higgs boson is puzzling, because quantum correction should make it much heavier unless some unknown physics precisely cancels these corrections. This fine-tuning problem motivates theories like supersymmetry, which proposes that every known particle has a heavier partner particle. These supersymmetric particles have not been found, leaving the mystery unsolved. String theory proposes that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings. These strings are incredibly small, possibly at the Planck scale, about 10 to the negative 35 meters, far smaller than atoms or even atomic nuclei. Different vibration patterns of strings correspond to different particles, just as different vibrations of a guitar string produce different musical notes. This elegant idea potentially unifies all of physics, including gravity, which has resisted integration with quantum mechanics in other frameworks. String theory predicts that spacetime has more than the 4 dimensions we experience. Most versions of string theory require 9 or 10 dimensions of space, plus 1 of time. The extra dimensions are thought to be compactified or curled up so small that we cannot perceive them. The way these extra dimensions are compactified determines what particles and forces exist in the observable 4-dimensional universe. With so many possible ways to compactify the extra dimensions, string theory may predict an enormous number of possible universes, each with different laws of physics. String theory has evolved over decades, with several different versions being proposed and later unified into a more comprehensive framework called M-theory. M-theory includes not just strings, but also higher dimensional objects called branes, which are like membranes existing in multiple dimensions. Our entire universe might be a 3-dimensional brane floating in a higher dimensional space. While string theory is mathematically elegant and potentially explains many features of particle physics and gravity, it faces significant challenges. The theory has not yet made testable predictions that differ from other theories. The energies required to directly observe strings or extra dimensions far exceed what any conceivable particle accelerator could achieve. Critics argue that without testable predictions, string theory is not yet a scientific theory in the traditional sense. Supporters counter that the mathematical consistency and potential for unification make string theory worth pursuing. String theory has led to advances in mathematics and has influenced other areas of theoretical physics. Whether string theory ultimately describes nature or remains a beautiful, mathematical structure without correspondence to reality is still unknown. The multiverse hypothesis proposes that our universe is just one of many universes, possibly infinite in number. Several independent lines of thought lead to multiverse concepts. In the eternal inflation scenario, the inflationary expansion that occurred in the early universe never completely stops, but continues in some regions forever. In this model, our observable universe is just one bubble where inflation ended, surrounded by an eternally inflating expanse that spawns countless other bubble universes. Each bubble universe might have different physical constants and laws, making them potentially very different from ours. The many worlds interpretation of quantum mechanics also implies a type of multiverse. In this view, every quantum measurement causes the universe to split into multiple branches, with each possible outcome occurring in a different branch. This creates an ever-branching tree of parallel universes containing every possible history. String theory's landscape of possible vacuum states suggests another type of multiverse, with each vacuum state corresponding to a universe with different laws of physics. The multiverse concept is controversial among scientists. Some argue that if other universes cannot be observed or tested, then their existence is a philosophical question rather than a scientific one. Others point out that the multiverse arises naturally from well-established theories like inflation and quantum mechanics, making it a legitimate scientific hypothesis, even if testing is difficult. The multiverse could explain the apparent fine-tuning of physical constants in our universe. Many fundamental numbers in physics seem precisely adjusted to allow stars, planets, and life to exist. Even small changes to constants, like the strength of gravity or the mass of the electron, would result in a universe unable to form complex structures. If countless universes exist with different constants, we naturally find ourselves in one that permits our existence, a concept called the anthropic principle. Critics argue that the multiverse explanation is unsatisfying because it gives up on finding deeper explanations for why constants have their observed values. The debate continues, with some scientists working to find observational evidence for or against multiverses, while others focus on alternative explanations for apparent fine-tuning. Space-time is not just a static stage where events occur, but a dynamic entity that can warp, ripple, and even be created or destroyed. Einstein's general theory of relativity revealed that gravity is not a force in the traditional sense, but rather the curvature of space-time caused by mass and energy. Massive objects create depressions in the fabric of space-time, like heavy balls placed on a stretched rubber sheet. Other objects moving through this curved space-time follow paths determined by the curvature, which we perceive as gravitational attraction. This geometric view of gravity has been confirmed by countless observations, from the precession of Mercury's orbit, to the bending of starlight during solar eclipses, to the detection of gravitational waves. Space-time itself has structure and properties that can be studied. Near black holes, space-time is so severely curved that it forms a one-way surface called the event horizon, beyond which not even light can escape. Inside a black hole, the roles of space and time swap in a sense, making it as impossible to avoid moving toward the singularity as it is to avoid moving forward in time outside. The Big Bang represents a moment when space-time itself came into existence. Before the Big Bang, there was no space, no time, and no before in the conventional sense. This makes the question, what happened before the Big Bang, potentially meaningless, like asking what is north of the North Pole. Space-time continues to expand today, with distant galaxies moving away from us as space itself stretches between us. This expansion does not violate the cosmic speed limit, because the galaxies are not moving through space faster than light. Rather, space between them is expanding. The rate of expansion is described by the Hubble constant, though recent measurements have revealed a tension between different methods of measuring this value, suggesting our understanding may be incomplete. Quantum mechanics suggests that space-time itself may not be smooth at the smallest scales, but rather granular or foamy, made of discrete units of space and time at the Planck scale. Unifying quantum mechanics with general relativity remains one of the greatest challenges in theoretical physics, requiring a theory of quantum gravity. The cosmic web is the large-scale structure of the universe, revealed by mapping the three-dimensional positions of millions of galaxies. When viewed from this cosmic perspective, galaxies are not randomly distributed but organized into an intricate network of filaments, sheets, and knots surrounding vast empty voids. This structure resembles a three-dimensional spiderweb or neural network spanning billions of light years. The cosmic web formed through gravitational instability over billions of years. In the early universe, matter was distributed almost uniformly, with only tiny density variations. Regions that were slightly denser than average had stronger gravity, pulling in more matter and becoming denser still. Over time, this gravitational amplification caused matter to flow along paths of least resistance, creating the filamentary structure we observe today. Dark matter provided the gravitational scaffolding for this structure, with normal matter falling into the dark matter concentrations to form galaxies. The densest knots in the cosmic web, where multiple filaments intersect, contain galaxy clusters, the largest gravitationally bound structures in the universe. These clusters contain hundreds or thousands of galaxies, bound together by their mutual gravity. The space between galaxies and clusters is filled with hot gas, often at temperatures of millions of degrees, that emits X-rays. Between the filaments lie cosmic voids, vast regions of space containing few galaxies. These voids can span hundreds of millions of light years across. While not completely empty, they contain far less matter than filaments and are dominated even more by dark energy. The expansion of the universe is accelerating fastest in the voids, causing the cosmic web to stretch over time. Computer simulations that include dark matter and dark energy successfully reproduce the observed cosmic web structure, providing strong support for our cosmological model. These simulations start with initial conditions based on the cosmic microwave background and evolve forward in time using known physics. The remarkable agreement between simulations and observations demonstrates that we understand the broad strokes of cosmic structure formation, even if mysteries like the nature of dark matter and dark energy remain. The Fermi paradox highlights the apparent contradiction between the high probability of extraterrestrial civilizations and the lack of evidence for them. The paradox is named after physicist Enrico Fermi, who supposedly asked during a casual lunch conversation, "Where is everybody?" The question becomes a paradox when you consider the numbers involved. Our galaxy contains hundreds of billions of stars, many with planetary systems. The universe is nearly 14 billion years old, giving time for civilizations to arise and develop. Even with slow interstellar travel, a civilization could colonize the entire galaxy in just a few million years, a blink of an eye in cosmic terms. Yet we see no evidence of other civilizations, no alien artifacts, no radio signals, no megastructures visible in telescope observations. This absence is puzzling and has inspired many proposed solutions. Perhaps intelligent life is extremely rare, with one or more steps in the emergence of intelligence having such low probability that we are alone in our galaxy, or even the observable universe. This explanation is called the rare earth hypothesis. Maybe technological civilizations inevitably destroy themselves before developing interstellar travel, through war, environmental collapse, or other catastrophes. Perhaps advanced civilizations exist, but choose not to expand or make themselves obvious. They might follow a principle similar to the Prime Directive in Star Trek, avoiding interference with less developed civilizations. Some speculate that advanced civilizations transcend physical existence, uploading themselves into virtual worlds or evolving into forms we would not recognize as intelligent life. Distance and time might explain the absence of contact. Even if civilizations are common, they might be separated by such vast distances and exist at such different times that they never encounter each other. The light speed limit makes interstellar communication and travel extremely challenging, potentially isolating civilizations. Another possibility is that we are looking for the wrong signals or in the wrong places. Our searches focus mainly on radio signals, but advanced civilizations might use communication methods we have not imagined. They might find radio as primitive as we would find smoke signals. The Fermi paradox reminds us how little we know about the prevalence and nature of life in the universe. The Drake equation attempts to estimate the number of active, communicative extraterrestrial civilizations in our galaxy. Proposed by Frank Drake in 1961, the equation breaks the big question into a series of factors that can be estimated separately. The equation multiplies together the rate of star formation in the galaxy, the fraction of stars with planets, the average number of planets that could support life per star with planets, the fraction of those planets where life actually develops, the fraction where intelligent life evolves, the fraction that develop technology detectable from space, and the length of time such civilizations remain detectable. When Drake first formulated the equation, almost none of these factors were well known. Today, we have much better knowledge of some factors. We know the star formation rate in our galaxy, estimated at several stars per year. We know from exoplanet surveys that planets are common, with most stars having at least one planet. We can estimate that perhaps 10 to 20% of stars have planets in the habitable zone where liquid water could exist. Beyond this point, however, the estimates become highly uncertain. We have only one example of life, here on Earth, making it impossible to know how likely life is to emerge on habitable planets. Some scientists argue that life emerges readily given the right conditions, pointing to how quickly life appeared on Earth once conditions allowed it. Others counter that the transition from non-living chemistry to self-replicating life might be extremely improbable. Even less certain is the probability of intelligent life evolving. On Earth, it took over 3 billion years for multicellular life to emerge after single-celled life appeared, and intelligence arose only very recently. This might suggest intelligence is rare, or it might simply reflect the time needed for evolution to explore biological design space. We also do not know how long technological civilizations last. Humanity has been detectable via radio signals for only about 100 years, a brief moment in Earth's history. If civilizations typically destroy themselves or lose interest in broadcasting within a few centuries, the number of detectable civilizations at any given time would be very small. Using optimistic estimates for unknown factors, the Drake equation might predict thousands or millions of civilizations in our galaxy. Pessimistic estimates could suggest we are alone. Fast radio bursts are mysterious astronomical phenomena, incredibly bright flashes of radio waves lasting only milliseconds. These bursts were first discovered in 2007 when astronomers analysed archived data from the Parkes Radio Telescope in Australia. Since then, hundreds of fast radio bursts have been detected, originating from distant galaxies billions of light years away. The extreme distances combined with the brightness of these bursts indicate they must release enormous energy, comparable to what the sun emits over several days, compressed into milliseconds. The origin of fast radio bursts remained mysterious for years, with theories ranging from evaporating black holes to alien signals. The breakthrough came when astronomers detected a fast radio burst from within our own galaxy in April 2020. This burst came from a magnetar, a type of neutron star with an extraordinarily strong magnetic field, quadrillions of times stronger than Earth's magnetic field. Magnetars occasionally produce enormous flares when their magnetic fields reconfigure, and one of these events produced a radio burst similar to those seen from distant galaxies. This discovery strongly suggests that at least some fast radio bursts come from magnetars, though other sources might also produce similar signals. Most fast radio bursts appear once and are never detected again, making them difficult to study. However, a few sources called repeaters produce multiple bursts over time. These repeating sources have been particularly valuable for scientific study because astronomers can train telescopes on them and gather more data. The repeating bursts show complex patterns, sometimes arriving in clusters, and sometimes showing periodicity, hinting at the physics behind them. Fast radio bursts provide tools for probing the universe. The radio waves from these bursts interact with gas and plasma during their journey across intergalactic space, arriving at Earth with slightly dispersed frequencies. By measuring this dispersion, astronomers can estimate how much material the waves pass through, providing information about the distribution of matter between galaxies. This could help locate missing normal matter that theories predict should exist but has been difficult to detect directly. Pulsars are rapidly rotating neutron stars that emit beams of electromagnetic radiation from their magnetic poles. As the neutron star rotates, these beams sweep through space like a lighthouse beam. When a beam points toward Earth, we detect a pulse of radiation, giving pulsars their name. The first pulsar was discovered in 1967 by graduate student Jocelyn Bell Burnell, who noticed radio signals pulsing with incredible regularity, once every 1.3 seconds. The signals were so regular that they were initially nicknamed LGM-1, standing for Little Green Men, before being recognized as a natural phenomenon. Pulsars rotate at rates ranging from once per several seconds to over 700 times per second. The fastest spinning pulsars, called millisecond pulsars, are thought to be old neutron stars that have been spun up by accreting matter from a companion star. As matter falls onto the neutron star from the companion, it transfers angular momentum, spinning the neutron star faster. Eventually, the companion may be completely consumed, leaving a rapidly rotating pulsar. The rotation rates of pulsars are incredibly stable, with some rivaling atomic clocks in precision. This stability makes pulsars useful for studying fundamental physics and testing theories of gravity. One famous example is the Hulse-Taylor binary pulsar, a system of two neutron stars orbiting each other. Precise timing measurements of this pulsar revealed that the orbit is gradually shrinking, exactly as predicted by general relativity due to energy loss from gravitational waves. This provided the first indirect evidence for gravitational waves decades before their direct detection. Some pulsars emit across the electromagnetic spectrum, from radio waves to X-rays and even gamma rays. These multi-wavelength observations help astronomers understand the physics of neutron stars and their extreme magnetic fields. The emission mechanisms involve charged particles accelerated to nearly light speed in the intense magnetic fields near the pulsar's surface and in the magnetosphere surrounding it. As pulsars age, their rotation gradually slows due to energy loss, and their magnetic fields weaken. Eventually, a pulsar spins too slowly, and its magnetic field becomes too weak to produce observable beams, and it fades from detectability. This process takes millions to billions of years. Quasars are among the most luminous objects in the universe, sometimes outshining entire galaxies while occupying a region smaller than our solar system. The name quasar is short for quasi-stellar radio source, reflecting their appearance as star-like points of light when first discovered. In the 1960s, astronomers measured the spectra of these mysterious objects and made an astonishing discovery. The spectral lines were shifted far toward the red, indicating enormous distances, and implying that quasars must be incredibly luminous to be visible at all. We now understand quasars as active galactic nuclei, powered by supermassive black holes at the centers of distant galaxies. As matter spirals into these black holes, it forms an accretion disk that heats to millions of degrees, emitting intense radiation across the electromagnetic spectrum. The gravitational energy released as matter falls toward the black hole powers the enormous luminosity, with some quasars emitting more energy than 1,000 galaxies. Quasars were much more common in the early universe than today. Looking at distant quasars, we see them as they existed billions of years ago, when the universe was young and galaxies were forming. The abundance of quasars in the early universe suggests that supermassive black holes grew rapidly during this era, possibly through mergers of smaller black holes and continuous accretion of gas. As galaxies matured and gas supplies dwindled, quasar activity declined. Many nearby galaxies, including our own Milky Way, have supermassive black holes at their centers. But these black holes are mostly dormant, lacking sufficient fuel to power quasar-like activity. If a large amount of gas fell into the Milky Way's central black hole, it could become an active galactic nucleus. though not as bright as distant quasars because the black hole is smaller. Some quasars produce jets of matter and energy shooting outward at nearly the speed of light from their poles. These jets extend for thousands of light years beyond the galaxy, powered by the rotation and magnetic fields of the accretion disk and possibly the spinning black hole itself. When a jet points directly toward Earth, we see a blazar, an even more luminous and variable source than typical quasars. Gamma-ray bursts are the most energetic explosions in the universe since the Big Bang, releasing more energy in a few seconds than the Sun will emit over its entire lifetime. These bursts were first detected in the late 1960s by satellites designed to monitor nuclear weapons tests, which noticed brief flashes of gamma rays coming from space. For decades, the origin of gamma-ray bursts remained mysterious. We now know that gamma-ray bursts come in two main types based on their duration. Short bursts lasting less than 2 seconds are thought to result from the merger of two neutron stars or a neutron star and a black hole. These collisions create a new black hole surrounded by an accretion disk, launching jets of matter and energy at nearly light speed. Long bursts lasting more than 2 seconds come from the collapse of extremely massive stars, similar to supernovae, but more energetic, sometimes called hypernovae. When a massive star's core collapses, if the star is rotating rapidly, it can form a black hole that launches powerful jets. These jets drill through the outer layers of the star and break free into space, producing a gamma-ray burst. If we happen to be looking down the jet, we see an extremely bright burst. If the jet points elsewhere, we might see only a supernova. This means gamma-ray bursts are beamed phenomena, visible only from certain directions, and many more occur than we detect. The afterglow of a gamma-ray burst, emitted at longer wavelengths like X-rays and visible light, can last for days or weeks. Observing afterglows quickly requires rapid response, so gamma-ray burst satellites alert ground-based telescopes within seconds of detecting a burst. These observations have confirmed that gamma-ray bursts occur in distant galaxies, often in regions of active star formation where massive stars are being born and dying. Gamma-ray bursts pose little danger to Earth at present because they are all very far away. However, if one occurred within our galaxy pointing toward Earth, it could be catastrophic, potentially stripping away part of the ozone layer and exposing the surface to harmful radiation. Fortunately, such events are rare, occurring in any given galaxy only a few times per million years. Space weather refers to conditions in space affected by the sun's activity, particularly the stream of charged particles called the solar wind, and explosive events like solar flares and coronal mass ejections. The sun constantly emits a stream of charged particles, mostly electrons and protons, that flow outward through the solar system at speeds of several hundred kilometers per second. This solar wind interacts with Earth's magnetic field, compressing it on the side facing the sun and stretching it into a long tail on the night side. Most of the solar wind is deflected around Earth by the magnetic field, but some particles enter the atmosphere near the poles, creating the auroras. Occasionally, the sun releases enormous eruptions of plasma and magnetic field called coronal mass ejections. These events hurl billions of tons of matter into space at speeds up to 3,000 kilometers per second. If directed toward Earth, a coronal mass ejection can arrive in 1 to 3 days, causing a geomagnetic storm when it collides with Earth's magnetic field. Strong geomagnetic storms can disrupt satellites, damage electronics, interfere with radio communications, and cause power grid failures. The most powerful recorded geomagnetic storm, the Carrington event of 1859, caused telegraph systems to fail and created auroras visible as far south as the Caribbean. If a similar event occurred today, it could cause trillions of dollars in damage and take years to fully repair. Solar flares are intense bursts of radiation from the sun's surface caused by the sudden release of magnetic energy. The radiation from a solar flare, traveling at the speed of light, reaches Earth in just 8 minutes. Strong flares can increase radiation levels in space, posing risks to astronauts and damaging satellites. The high-energy particles from flares also disrupt radio communications, especially at high frequencies. Space weather follows the sun's 11-year activity cycle. During solar maximum, when sunspot numbers peak, space weather events become more frequent and intense. During solar minimum, the sun is quieter, though significant events can still occur. Scientists monitor the sun continuously from spacecraft and ground-based observatories, providing warnings of incoming coronal mass ejections and solar flares. These warnings allows satellite operators and power companies to take protective measures. The habitable zone around a star is the range of distances where a planet could have liquid water on its surface, generally considered essential for life as we know it. This zone depends on the star's luminosity. Around hot, luminous stars, the habitable zone is far from the star. Around cool, dim stars, it is much closer. For our Sun, the habitable zone extends roughly from the orbit of Venus to a bit beyond Mars. Earth sits comfortably in the middle of this zone, though Venus experienced a runaway greenhouse effect that made it hellishly hot, demonstrating that being in the habitable zone is necessary but not sufficient for habitability. Many factors besides distance affect whether a planet can support liquid water and possibly life. The planet needs sufficient mass and gravity to retain an atmosphere. Too little gravity and atmospheric gases escape into space. Mars, with only 38% of Earth's gravity, lost most of its atmosphere over billions of years. Too much gravity, and the planet might retain thick atmospheres of hydrogen and helium like Jupiter, creating crushing pressures unsuitable for surface life. Plate tectonics may also be important for long-term habitability. On Earth, the carbon cycle regulated by plate tectonics helps stabilize climate over geological time. Without this mechanism, carbon dioxide might accumulate in the atmosphere, causing runaway warming, or become locked in rocks, causing runaway cooling. A magnetic field helps protect the atmosphere from erosion by stellar wind. Earth's magnetic field deflects much of the solar wind, while Mars lacks a global magnetic field and lost its atmosphere. However, Venus also lacks a strong magnetic field yet retains a thick atmosphere, so this factor is not absolute. The concept of the habitable zone has expanded with discoveries suggesting life might exist in environments once considered impossible. Moons like Europa and Enceladus have liquid water oceans beneath their icy crusts. Far outside the Sun's traditional habitable zone, tidal heating from their host planets keeps these oceans liquid. This suggests that habitable environments might be more common than previously thought, not limited to planets at the right distance from their stars. Terraforming is the hypothetical process of transforming another planet to make it habitable for humans without life support systems. Mars is the most commonly discussed candidate for terraforming because it has many favorable characteristics. A day length similar to Earth's, water ice at the poles and underground, and evidence of past liquid water. Terraforming Mars would require dramatically increasing the atmospheric pressure and temperature. Mars's thin atmosphere, less than 1% of Earth's pressure, cannot support liquid water on the surface, and temperatures average -63 degrees Celsius. Various methods have been proposed to warm Mars and thicken its atmosphere. One approach involves releasing carbon dioxide frozen at the poles and in the soil, creating a greenhouse effect to trap heat. This could be achieved by placing mirrors in orbit to focus sunlight on the poles, by darkening the ice with dust to absorb more heat, or by using nuclear devices to vaporize the ice. Another proposal suggests impacting Mars with ammonia-rich asteroids, which would add greenhouse gases and potentially deliver water and nitrogen. Even more ambitious ideas include establishing genetically engineered microbes on Mars to produce oxygen and nitrogen through photosynthesis, gradually building up a breathable atmosphere over thousands of years. However, terraforming faces enormous challenges. Mars's low gravity means it would continuously lose atmospheric gases to space, requiring constant replenishment. The planet lacks a global magnetic field, leaving any new atmosphere vulnerable to erosion by solar wind. The total amount of carbon dioxide available on Mars may be insufficient to create the necessary greenhouse effect. Even if technically possible, terraforming would take centuries or millennia and would be enormously expensive. Some argue that before attempting to terraform Mars, we should perfect techniques for managing Earth's climate. Others question the ethics of potentially destroying any indigenous Martian life, should it exist, or of fundamentally altering another planet. Nevertheless, thinking about terraforming helps us understand planetary processes and might someday become relevant if humanity becomes a multi-planet species. The search for technosignatures represents humanity's attempt to find evidence of advanced extraterrestrial civilizations through their technology. Unlike searching for biosignatures which might indicate simple life, technosignatures would definitively prove intelligent life exists elsewhere. The most famous technosignature search is SETI, the search for extraterrestrial intelligence, which primarily looks for radio signals from space. Radio waves travel at light speed and can cross interstellar distances with minimal absorption by interstellar gas and dust, making them an efficient means of communication. SETI uses radio telescopes to scan the sky for signals that stand out from natural astronomical sources. Natural sources produce radio noise across a broad range of frequencies, while an artificial transmitter would produce a strong signal at a specific frequency, appearing as a spike in the data. Despite decades of searching and examining billions of frequency channels from millions of star systems, no confirmed artificial signal has been detected. The famous WOW signal detected in 1977 remains unexplained but has never repeated, leaving its origin uncertain. Beyond radio signals, scientists have proposed searching for other technosignatures. Optical SETI looks for laser pulses that an alien civilization might use for communication. Such pulses could briefly make a star appear brighter, distinguishable from the star's steady light. Another approach looks for megastructures, enormous engineering projects that advanced civilizations might construct. The most famous concept is the Dyson sphere, a hypothetical structure surrounding a star to capture its energy output. A complete Dyson sphere might be impractical, but a Dyson swarm of orbiting solar panels could achieve the same goal. Such a structure would absorb visible light and re-emit it as infrared radiation, creating an unusual spectral signature. In 2015, unusual dimming patterns of the star known as Tabby's star led to speculation about a possible megastructure, though natural explanations involving dust clouds now seem more likely. Future technosignature searches might look for industrial pollutants in exoplanet atmospheres, or for evidence of artificial lighting on the night sides of planets. The absence of detected technosignatures could mean civilizations are rare, far away, quiet, or extinct.